The interquartile range of a box and whisker plot is a relatively rare measure of the dispersion of values around the center of a distribution. The most widely used measures of dispersion are variance, standard deviation, and standard error. So we're going to talk about variance in this video, and then shortly thereafter we'll talk about standard deviation and standard error. So variance, I've got on the whiteboard here already, is denoted with this symbol here. So it's the lowercase Greek letter sigma squared. That squared is key. So overall, this sigma squared, that denotes variance. And you can define variance with expected value notation, but I think it's easier to understand without it. So we'll define it this way here. So at its core here, inside the brackets, we take any individual data point I from our distribution, and we subtract from that individual data point the mean, right? So we already covered mean a little while ago in these videos, and we noted how that bar above the vector of the distribution that we're taking the mean of is how we indicate mean. So any given instance from our distribution, from our vector of values x, and then we subtract the mean from that individual value. And then we square it, and we sum up across all of those individual instances. So we take each instance, subtract the mean from that instance, square the difference, sum up across however many instances we have, and then we divide by n, which is the number of instances that we have. An astute follower of the other subjects in my Machine Learning Foundation series, so the linear algebra and calculus subjects, might notice that this formula is the same as mean squared error that we use in machine learning, with the big difference here that instead of comparing an individual observation with the mean of the observations, with mean squared error, we compare an individual observation, typically an output from a model, which would be denoted as y, not x. But that output from a model, we'd compare it with the correct output from the model. So we'd be comparing what we call y hat with the true y. Anyway, that's just a quick aside. There is, this formula for variance does look a lot like mean squared error. You're right. Now, technically speaking, one thing to note here is that we should be actually dividing by n minus 1. So the formal definition of variance has n minus 1 in the denominator, and that's related to something called degrees of freedom, which we'll be talking about shortly. But with the large data sets that are typical of machine learning, whether we divide by 1,000 or 1,001, it makes a negligible difference to variance. If you were working with a small number, like 8 data points, which is pretty rare in machine learning, then it would matter a little bit, right? Also, technically speaking, the variance of a sample is typically actually denoted with s squared, not sigma squared, akin to the same way that x bar is the mean of a sample, where mu, the Greek letter mu, is used for the mean of an entire population. Technically speaking, this variance notation that I'm using here of sigma squared, that would, in a strict statistics textbook, that would be used for only the population variance, and you would use s squared for the sample variance. But we see this used a lot in machine learning literature, so I'm going to denote variance this more common way in machine learning world. Okay, as an example of how we calculate variance in this hands-on code demo, we'll use the PDF, the probability density function x from earlier, So we've already been using that distribution a lot in this notebook. Most recently, we saw this box and whisker plot of it, and we plotted it out here. So we're going to be using that same distribution x again. So to calculate variance, so we've got the equation here for convenience. We're going to need x bar, the mean of the sample. So here it is. The mean value is 0.82. And then next we can calculate all of the squared differences. So I'm using a list comprehension here to iterate over each instance of x in our vector x. So there's 1,000 data points in this vector. So we're going to iterate over each individual element I in that vector x. And for each of those elements, we'll subtract the mean x bar from that xi and square it. So that will give us our squared differences. And that corresponds to this part of the equation here, xi minus x bar squared. So we get a list of our squared differences, and here's a look at the first 10 squared differences. Now we can sum them up and divide by however many instances we have, and that will give us our variance. So that corresponds to the rest of this function, right? So after we have our squared differences, we sum them all up and we divide by however many we have, and that gives us our variance. So, yeah, sum them up, divide by however many there are, that gives us sigma squared, our variance. So our variance comes out to about 0.4 for our distribution x. Now, you don't have to calculate variance with this many steps every time you do it. I just wanted to show you exactly how variance is calculated, but there is a built-in NumPy method, so you can simply call this var variance method, pass in your vector of values in your distribution, and voila, you get the same value as we did. All right, so that's variance, our first measure of the dispersion of a distribution. Up next is the standard deviation.